Hello, everyone. Good morning. Yeah, it's my great pleasure to speak here. So I'm going to share with you some of the latest developments in the area of generative AI for sound generation, in particular with text as condition. This is a joint work with many of my PhD students, postdocs, and colleagues. I show some of the names here, and funded by EPSRC and British Council. And here is the outline of my talk. First, I introduce the problem and also briefly discuss some of the well-known models in audio generation and particularly generative AI models. Of course, I'm not going into details, but just show you what are out there. And then we will introduce some of the models we have developed. These are popular models. Many people are using that. For example, Audio ADM and Audio ADM 2, and Wave Journey, Wave Caps. This is a large-scale data set. So the other three are audio generation models. You can find them online. Actually, it's all on GitHub and Hugging Face. You can play with these tools, see how good it is. Then I will conclude the talk and also invest in some of our future work. If time allows, we will also show a few demos about some other related work. Audio generation, why we need audio generation? So audio generation is essentially like creating a computational phony artist. So it's basically in many conventional tasks like game design and movie and audio production, we do need to generate audio. Otherwise, you would have to capture audio from the real world, right? And capture audio from real world sometimes very expensive. And for example, you have to go to particular scene to capture particular sound events. And in some scenarios, this sound event might not be existing in the real world. So can we actually use a software to generate automatically? And that will save time and also cost. Another thing is content creation. For example, we can actually compose music, right? And often this is done by musicians, but now we could actually use software to do that. And audiobook, and also white noise for meditations. Another very popular use case is that nowadays we are actually developing large-scale machine learning models, but machine learning needs data to train the model, right? So collecting data often is a very expensive and timely process. So can we actually use tools to generate data? For example, for creating these audio models, we could actually generate data using some software, and then we can use this data as a way to augment your data set. So that's the examples of use cases. So in terms of audio generation models, historically, we are using these so-called mathematical models or physics-based models where you have an equation to describe the process. For example, the popular harmonic models, sinusoidal models, you just tune the amplitude, frequency, and the phase information. You can generate sound, right, for pure tones or harmonic sound. But the limitations with this conventional model is that you have to build the models for example, for each individual sound, or for example, for piano, you have to build a model for piano sound. And this actually makes it very complicated because some sound is very, very difficult to build physical models. So that's to address these limitations, we could use data-driven models where you use neural networks, you use machine learning, and then you have this labeled data. And use labeled data, you can train the model so that the model is able to describe the data, right? So this is a data-driven model, and one of the now widely used this model is called generative models. So now I'll give you a very brief idea about what is generative models. Essentially, what we are trying to do here is, given a set of data we call training data, we want to create a model. In this case, is a generative model, which is able to approximate the underlying distributions of the data we have here, right? So we use PXX to denote the underlying distribution. So in the training process, we try to estimate such distribution. And in the inference stage or in the generation stage, we can use this trained model to sample and generate new samples based on this distribution, right? So in the learning process, we try to find the distribution of the data. And in the generation stage, we try to use this distribution. We can sample from this distribution the individual samples of the audio signal. So that's how we do in terms of generative AI models, right? This is just in concept how this is done. But of course, in practice, this can be much more complex depending on what type of distribution you are using, what you try to estimate from data. So we have, for example, conditional generative models. We have these likelihood models, popular likelihood models, autoregressive models, flow-based model like normalization flow, and variational autoencoders, adversarial models, diffusion models. So this is all popular models in the literature. And I just give you a few examples. I'm not going to go details about each of these models. For example, conditional models, so this is very widely used, where you instead of just learn the underlying distribution, we actually plug in the condition C. Condition C here, right? The condition C, so we are actually learn this conditional probability, PXXC. C is the condition. The condition could be anything. For example, in audio generation, it could be, sound classes, like dog barking, like bird chirping, right? And in music, it could be, for example, instruments, or timbre, or MIDI notes, right? In the speech, it could be accents, or it could be language. So the condition could be anything. And the image, people also use the labels or bounding boxes as conditions to, so basically we have learned this conditional probability. And then in the generation stage, we can plug in this condition as, for example, one hot vector, whatever information into the conditional probability. Then you can sample this conditional probability to generate new audio samples. And the likelihood model, instead of learn this underlying distribution, we actually learn this likelihood distribution, which is Px theta. Theta here is the model parameter. For example, if you use neural network model, then theta is the parameters of the neural network, right? So basically, we are actually trying to create a model so that the sample is likely to be generated by this model. So basically, we actually try to maximize the likelihood that this sample X is generated by this particular model. So I try to find the parameter theta, the optimal parameter theta, so that we can use this model to generate this data. So typical example is autoregressive models, flow-based models. Autoregressive model is basically, you generate a sample one by one. So to generate the current sample, you need the samples from the previous time instance. And variational autoencoders is also very popular, where you have this encoder and the decoder architecture, where you can turn the data into latent space using an encoder, and then in the decoder you generate samples based on the embedding in the latent space for each individual samples. So that's the idea for likelihood-based models. Adversarial model is also very popular. So the idea is that you actually learn two networks. One is called generator, the other one is called discriminator. So the generator actually try to produce examples according to the data distribution given the latent vector Z. The latent vector Z is essentially the compressed representation of your data, for example, the features, right? And the discriminator is trying to distinguish between the generated examples and the real examples. So this is essentially the minimax game. Essentially, the generator is trained to minimize the loss function, and the discriminator try to maximize, right? So this type of model has been very popular. For example, GAN. Many people have used that for image and video generation, and also for sound generation. But this method, the limitation is that it's not actually able to capture the distribution of data. And also, the training stability could be an issue. So nowadays, the state of the art is given by this so-called diffusion model. So diffusion model is based on this so-called stochastic differential equations. And this is the general process. Basically, you have a forward and backward process. The forward process, where you actually, based on the clean data, for example, in our case, it's audio signal. Clean audio signal, you add scheduled noise until it becomes a Gaussian distribution. It's a random noise, right? And then in the backward process, you try to denoise the data and turn from this noise back to a clean signal. So the learning process here is that we try to optimize the model so that we get the optimal parameters of the model that is able to allow the model to estimate the noise in each step, how much noise you added, right? For example, in the forward step, you add a little bit noise, and then you actually estimate how much noise I added into the signal. Because if the model is able to estimate the noise, then it's able to denoise the signal, right? So that's how it works. So we try to find out the optimal parameters of the model so that it's able to denoise the signal. Eventually, we can actually reconstruct the clean signals from the noise. So this is the general process of a diffusion model, and it's very popular now and used widely in image, video, as well as sound generation. So our work is mainly based on a diffusion model that we will discuss next. So here we are going to focus on text to audio generation. It's basically is a conditional generation model where we have the condition from text, text descriptions like the prompts, right? Often used like in ChatGPT, where you type a sentence or paragraphs, and then you tell the system what you want to generate. I want to generate a dog barking or birds singing, right? And then the system is able to generate the sound for you. So that's the idea. And of course, while we're doing this, text can be actually bridged, for example, between audio and other modalities like image and video. But it also allows users to very easily play with the system. There are some related work here. For example, initially, we did some work on neighbor to audio generation based on classes. For example, sound classes, dog barking, bird chirping, these sound classes. It's not a language description, just individual text. And then in 2022, we start to have systems to actually generate sound based on text descriptions. For example, TIFF sound, audio gen, and making audio. And then text to music, there are also some work out there. Music IRM, noise to music, for example. There are also other systems out there like audio IDM, sing-song, so plenty of systems developed in recent few years. And neighbor to audio generation, this is the work we have published in 2021, where we can take the sound classes as condition, we generate the sound for you, right? This is a system we built. So basically, this is the detail how the system works. So we have the condition. We actually train a so-called autoregressive model that is able to generate the latent representations. And the latent representation after it's generated, we can use a so-called convolutional decoder to generate spectrograms. And then the spectrogram can be turned into waveforms using a waveform decoder. For example, we could use half a gram. So that's how the overall system works. And here, we also trained a so-called versional autoencoder. This is a VQVAE. So basically, we train a model to learn to reconstruct the original audio. So this is the original audio, and this is a reconstructed one. Here we have the encoder and the decoder. So the encoder essentially give you latent representations. This is a compressed representation we call Z. And then we use this quantization. Basically, this is a code work. Based on the code words, we can compress this representation into this discrete time frequency representation. And then we can use the decoder to reconstruct the data, reconstruct original audio signals. Why we do this? Because by doing this, we can actually get this decoder so that you can generate sound, for example, spectrogram based on latent representations. So that's why we can use this here to generate spectrograms. And the condition is built into the autoregressive model. It's also trained using some data. So this is the model we developed in 2021. And but now I want to focus more on text to audio generation based. So the text is a natural language description. This is the audio LDM model because it's a more advanced model. So we'll discuss a little bit more about how this model works. Basically, in this model, we have so-called pre-trained encoder. This is a clap encoder. How this works? Essentially, we try to map the audio and the text description into a joined latent space. So you have some audio data. Each audio sample has a paired text description. For example, audio signal with text description to telling you what's in the audio, right? So this is paired data. We use the paired data to train a model we call clap encoder. So it's a contrastive language audio learning model, and and this model is essentially try to actually map this audio and text data into the joint space, and then we train this latent diffusion model. The latent diffusion model is essentially a self-supervised learning method where you take the embeddings and you can actually learn to, for example, to denoise and then to reconstruct the original. I mean, it's the model we have discussed earlier. But here we are doing the latent space because, it's much faster as you do the original sample domain. Original sample domain is pretty close. So in the inference stage or generation stage, we only need the text information because this clap model is already pre-trained. We take this text this is vectors, from the text encoder as a condition to this latent diffusion model, which is already trained, and then we can generate the latent representations of the original audio signals. So this is a general process. Okay, there's a little bit more details about how we map the audio and the text into the joint latent space. Basically, we have the audio data, we have the text data, and then we can map into this joint latent space using, for example, cosine similarities or something similar to measure how they are close to each other. And in terms of latent diffusion model, this is how we train them. So basically, we have the audio examples, and then we train to reconstruct the audio examples, and then the model parameters are optimized based on this process. And I show you some examples. The more details you can find from papers. And of course, there are several advantages. One of the main advantages is the computation is very fast as compared with all the other existing systems available in the literature because it's done in a latent space. And also, it can be used for many other downstream tasks. For example, style transfers, or super resolution, or in-painting, because you can easily modify the conditions in the latent diffusion model. Here we have some example, the performance the performance. Basically, we measure the performance in terms of objective evaluation metrics, as well as subjective evaluation. Subjective evaluation, we have to get people to listen to the sound, see how good they are. And here we have some performance metrics. You can see that our model, audio RDM, is the, in terms of size, is relatively small, especially for the small model. And in terms of performance, is also given the state-of-the-art result. And this model, you only need one GPU to train, so it's very fast. Could you play some sound? Basically, look at the text, and the sound is generated by So you get some idea, right? The text description in these few examples, we actually import a question to ChatGPT, and the ChatGPT gives us this answer. This is a text, and then we input this text into our system. So the sound you hear just now is generated by our system. So you take the text as input, you generate sound. So clearly, the system is able to capture the semantic information from the text descriptions. And then we generate sound which is closely match the text description. And now it's used by many people. You can see from Hugging Face, one of the top apps in more than 100,000 apps in Hugging Face, and is always top 50, if I remember correctly. And more recently, we have further developed this system into the second version, which is called Audio RDM 2, where the main difference is we have so-called language of audio representation, where we take many different conditions as input. For example, not just text, but also image, video, and some other, input like audio itself, for example, as conditions. Then we can use the similar process to generate sound. And so I'm not going into details, but basically it's very similar to audio RDM in terms of the latent diffusion model we developed here. So there's a big change here in terms of what condition you can take by the system. And now we allow the system to take many different type of conditions. And also, and the model developed now is we could call the foundational model because it's generic. It can be applied to many different type of data. And this architecture can be easily adapted to many different tasks. So some people actually are using this model for other tasks like speech enhancement, audio style transfer. So you can do that actually with the same model. And here we have another demo. It's about 3 minutes. I think we probably just hear the beginning part. later part of the demo, what is Wenwu Wang, I just show you and later.
The Secret Service did not, at the time of the assassination, have any established procedure governing its relationships with them. The prisoners were in due course transferred to Newgate to be put upon their trial at the Central Criminal Court.
Well, if you want to really grow kind people, there's a lot you can do when things are good, when you are full of joy. What we grown-ups might call restitution. If you break something, you fix it, whether it's a broken toy or hurt feeling. If any...
I have to move on for time consciousness there. So here is another tool we have developed. It's called compositional sound generation, where you can actually compose different elements in the audio signals. You can actually also considering the temporal order, for example, which sound events earlier, which later. So you have more controls. You can, this is the code available online, and the idea is that you can actually write the audio scripts, and then you have the code to run for each individual model. You can build library of models, and then you generate sound based on library of models. This could be used for storytelling. If you want to write audio stories, then this is the right tool you can use. And another work we have done is creating a large-scale data set that is useful for such applications. For example, wave caps. So I'm not going into details. You can have a look. So just to summarize, we have discussed text-to-audio generation. So in terms of the next stage of work, we are interested in building this physics and data-driven model. Is a joint model because text-to-audio generation using AI models, it seems like it's difficult to control in some cases. For example, what exactly you want to generate, there's less control there. And the physical models, you might have more controls there. So we want to leverage the advantage of these two models to build stronger models. And I just want to show you another couple of examples related to this work, but could be quite interesting for some of you. One is so-called sound separation, where we can actually separate this individual sound from a mixed sound based on text descriptions. Here we have an example with a mixed sound, and then if you input a human query, for example, engine sound of a vehicle, then the system is able to separate these individual sound from the mixed sound. So can you play the mixture?
Random. So I've just made two methods. Haven't really created them, but this is how I'm going to deal with them. And before I...
Can you hear that this is the mixed sound with the engine sound plus person is talking, right? Now, if the input to the system said the engine sound of a vehicle, then you get the engine sound. Okay, that's the sound separation. And we also have shared the work online. You can find the code and demos there. And another piece of work we have done is on sound recognition. And for example, scene classification, audio tagging, sound event detection. So I show you a demo. This is a system we developed. It's called PANS, which is able to recognize what's in the sound. Here we show each sound event in terms of probability. This number is the probability estimated based on this sound. So for example, music has the highest probability in this particular sound. You can see the changes of the probability. Yeah. Please play the sound.
Okay, no more. No more. Okay.
horse.
A high school girl's been murdered. Mr. Harrison's daughter is missing.
Okay, that's all. Sorry, I probably have overrun. Thank you so much.
Wenwu Wang!